Simpsons Rule is really a spin-off of the trapezoid rule. To be honest, I didn't know the person, but it was a mathematician. I'm sure his last name was Simpson. And he kind of took the trapezoid rule and manipulated it a little. Okay, he manipulated the trapezoid rule. I'm not going to copy it down. And I'm also going to share with you that you don't need to memorize it. By the way, you do need to memorize the trapezoid rule. But make sure that you can see it in the book and that you can do a couple problems with Simpsons Rule. If you look at it in the book with me, it's kind of interesting what they've actually done. What he did is instead of just taking the standard y values in the middle, in other words, 2 of each y value in the middle, it's kind of like he took 3 of each y value with a little bit of oscillation. Okay, when I say 3, I'm talking about the average. He took 4 of a y value, then took 2 of the next one, then 4 of a y, then 2 of the next one. So there's this oscillation of 4, 2, 4, 2. What that essentially averages out to is that there's now 3 of the y values. And that's why you see that we're dividing by 3. To sort of counteract that, we have h over 3. Okay, now Simpson's rule requires us to very carefully follow this 4-2-4-2 pattern. And let me show you how that can work out with one simple example. You guys will have to do this in the assignment. Okay, but like I said, you will not need to memorize it, which is kind of code for you won't have to do it on a test. It's still important, but I think we can take care of it in an assignment format. Now the directions would say something like, and I should have wrote this down, use Simpson's rule. Let's change this here. Use Simpson's rule to find, and then it's okay for us to use the integral sign. So use Simpson's rule to find the integral with n equals, we're going to use 4 again. Sometimes people are kind of like, what's up with the n? How do I know? It has to be given to you. Okay, unless in the case of our little project you're going to do at Desmos, you have to make up your own n. Okay, but basically we can divide it into as many subintervals as we want to. Now, even though we're not making trapezoids, it's kind of like we still have 4 regions. Those 4 regions denoted by n equals 4. And that means that my height, in other words, the length of each subinterval, is going to be my total length, which is denoted by 5 minus 3, but divided into 4 equal spaces. So, of course, we end up with 2 over 4, which is just 1/2. So it's kind of like each space has a size of 1/2. As we tried to emphasize yesterday, that 1/2 is very important for us to get our y values, because of course it's going to help us to get the x values. And this is good practice for any type of problem where we realize that we're going to go from 3 to 5 by halves. We're going to go from 3 to 5 by halves, which of course means we'll be at 3.5, then 4, then 4.5. Now, I'm not doing anything with a sketch, which I have to admit, even for me, kind of bugs me, but there's this graph. It's the graph of 2x cubed. Okay, maybe you can kind of picture that graph, maybe not, but it's got x values, which then correspond to y values. Of course, found by plugging into this equation. Okay, yes, I'm going to give you some of these, but you should be at least think about them, make sure that you're on the same page. If you cube the number 3 and then double it, that's double of 27. So for me to write the number 54 right here shouldn't be a big shocker. If you plug in 4, of course you cube it, that means you're going to get 64. But if you double 64, I believe we're at 128. And so you can see how we're getting these y values. Okay, there's a couple of them that you couldn't get without a calculator. That's fine. I tend to write the decimal down because I also, again, just popped it in a calculator, but 85.75 and 182.25. Numbers are big. That's because the equation is of a larger variety, 2x to the third power. Okay, so we're probably going to get a pretty big area, but let's use the Simpsons rule to find it. Now, I only showed it to you in the book. I know some of you weren't able to look at it in the book, but basically Simpsons rule starts out in a similar fashion to the trap rule, h over. Now, again, this is probably the most common mistake where people put h down and it already looks like it's over, like 1 over 2, but it's supposed to be h over 3. For Simpsons rule, it's over 3, so it's 1/2 over 3. And then we kind of get like this little oscillating pattern. Okay, now it always starts off with just a single for your first y value. And the truth is it always ends with a single for your last y value. But it's the y values in the middle. It always has to follow that 4, 2, 4, ... pattern. So it's going to be 4 of my 85, 75. It's going to be 2 of my next one. So 2 of my 128. It's going to be 4 of the next one. So 4 of 182s. And I really didn't get to say this yet, but I want you to notice through this one example that it always also has to end. It has to end with a 2, 4, 1. So it begins with a 1, 4, 2, but it has to end with a 2, 4, 1. And sometimes people say, well, what if it doesn't? Well, it will, because the number of subintervals will always have to be even. The number of subintervals will always have to be even. And I'll just kind of say nicely, just trust me. You don't have to think about it too much, and it will work out as long as n is even. Okay, so we start with 1, 4, 2, but we end with 2, 4, 1. So all is well. Okay, most of this is calculator work. I know you guys can do that. As I said yesterday in the lesson, you have to write down at least one set of information. Some people will write down what I wrote down and put the rest in their calculator. Some people will put in their calculator and then write down some of the answers that happen, like 1/6 and 1632. But everybody, make sure you write down the final answer. So we get 272. The highway that runs from, of course, Lancaster to the Buck and back, 272. One more thing about 272. Okay, remember how yesterday we found the actual answer? Let's find it today. I'm going to choose to show you, to use FNINT. It's kind of one of those things that sometimes people aren't sure if they're allowed to use, which is good. I don't want you relying on your calculator too much, but it's a tool that you should understand that if you are asked to find an actual integral, which is what we've done most of this chapter. 3 to 5. So if I'm asked to find an actual integral and I pop out or whip out the FNINT, okay, does the work for you. And we see one kind of little interesting nugget of information for today. And that is that Simpsons Rule, I have it up here, is perfect for cubics. Simpsons Rule is perfect for cubics. And it's kind of why it was, again, I don't know the mathematician, but why Simpson messed around a little bit. So if you happen to have a function that's of the cubic variety, Simpson's rule is not really an estimation, but it's an actual. It's funny, for parabolas, yesterday's problem, We don't have a perfect estimator. If it's a parabola, the trapezoid rule and or Simpsons rule will not be perfect, although it'll be close. Okay, but anyway, Simpsons rule is perfect for cubics. Everybody happy? You're thinking about that eclair. I know, it was good. Oh. All right. Then you have what I would traditionally call like a work period, which will kind of flow a little bit into tomorrow. Again, for the book assignment that's due tomorrow, and then the little project that's due by midnight tomorrow.